In this video, I will explain how to represent a 3D vector and Cartesian coordinate system, how to find the magnitude and coordinate angles of a 3D vector, and finally, vectors addition and 3D space. The operations of vector algebra are greatly simplified if the vectors are first represented in Cartesian vector form. The concept of unit vector is very significant here. For example, vector A having magnitude A, then unit vector can be defined as UA equal to vector A divided by its magnitude. Unit vector has magnitude of 1 and it is dimensionless. It points in the direction is the original vector A. The unit vector in the Cartesian axis system are I, J, and K. They are unit vectors along the positive x, y, and z axis respectively. Consider a box here with side ax, ay, and az meters long. The vector A can be defined as A equal to ax plus ay plus az in the I, j, and k direction. The projection of vector A in the xy plane is A prime, so the magnitude of A prime is found by using the same approach as 2D vector, such as A prime equal to ax squared plus ay squared whole under the root. The magnitude of the position vector can now be obtained from this equation. The direction or orientation of vector A is defined by the angles alpha, beta, and gamma. These angles are measured between the vector and the positive x, y, and z axis respectively. Their range of values are from 0 to 180 degree. Using trigonometry, direction cosines are found using these equations. These angles are not independent. They must satisfy the following equation. This result can be derived from the definition of coordinate direction angles and the unit vector. Recall the formula for finding the unit vector of any positive vector, or written another way, unit vector of A equal to cos alpha plus cos beta plus cos gamma. Once individual vectors are written in Cartesian form, it is easy to add or subtract them. The process is essentially the same as when 2D vectors are added, such as the resultant force vector Fr equal to summation of all forces, which is further equal to summation of all x components plus y components plus z components of the force. For example, if there are two vectors A, which is equal to ax plus ay plus az, and vector B, which is equal to bx plus by and bz, adding them up will give you ax plus bx, ay plus by, and az plus bz in the k direction. Similarly, the subtraction can also be carried out. Sometimes 3D vector information is given as magnitude and the coordinate direction angles, or magnitude and projection angles. Notice the difference between coordinate direction angles and projection angles. You should be able to use both these types of information to change the representation of the vector into the Cartesian form, such as F equal to 10I minus 20J plus 30K Newton. Let's consider this example. Two forces are being applied, F1 and F2, to a hook, and it asks you to find the resultant force in Cartesian vector form. So our plan is to use geometry and trigonometry. I will write Cartesian vector forms of F1 and F2, and then we add the two forces to get the resultant force. First, resolve force F1 into its three components. The x component is 0 pound, y component is 400 pounds, and z components become 300 pounds. Now write F1 in Cartesian vector form. Don't forget the units. Vector F1 is equal to 0I plus 400J and plus 300K pound. Now resolve the force F2. We are given only two direction angles, alpha and gamma. So we need to find the value of beta. Recall this relationship. Now substitute what we know, solving for the unknown beta, which is equal to 75.5 degree. Now that we have the coordinate direction angles, we can find unit vector. So using the unit vector equation, we can write the F2 vector, which is equal to 712.8 I plus 200.3 J minus 608.3 K pounds. Now adding the respective components of these two vectors, we get a resultant vector R, which is equal to 713 I plus 600 J minus 308 K pounds.